me to talk about such an important topic of space camera. It's a very state-of-the-art technique, and you know a lot of applications about this radar, but without knowing the instrument, you cannot fully utilize it. So my honors here is to explain how this instrument actually works. So this is a quite a complicated instrument in the sense that it needs knowledge of electromagnetic field theory, it needs the knowledge of communications, and it needs the knowledge of signal processing. So anyhow, I try my best to avoid mathematics as far as possible. Only some elementary mathematics when it is absolutely needed I took its help, but this is rather awareness program and not a specific instrument building systems program. So I try to talk and limit my talk to a very simplistic. So as it is said that ST radar awareness program, ST radar. ST radar. Radar is nothing but a phased area radar. Phased area radar. How it works, I will explain in my next slides. So I will divide my talks into the introduction of phased area radar and then how the digital beamforming technique, which is the main technique which is utilized in this phased area radar, is actually worked. Then digital beamforming receiver, how it works, that I will explain, and a few applications. Most of the application has been already narrated by Professor Paul, and to my limited knowledge I will tell something about it. So this is a typical, there are different types of radar existing presently. I put some of the things: pulse radar, scanning radar, frequency modulated continuous wave radar, MTI, moving target indication radar, and SFCW radar, which is called step frequency continuous wave radar. All this radar has a single antenna architecture like this. We have a dipole element, which is the transmitting element here, and a beam reflection. The signal goes here and reflects and goes to the target. So once it hits the target, the echo comes back and it receives again in a backward fashion. It comes back, it is reflected and put into the feed, and it is taken out and it is here. This is how this kind of radar works. So it's a simple one feed, one antenna is utilized. But the present radar, ST radar, which is a phased array radar, this consists of array of antennas. You see, instead of a single feed, we have several feeds. And as it is mentioned earlier, that we have 475 such kind of feet or elements of antennas, which is actually what I will come to those points. The beauty of such kind of arrayed antenna system is that we can form a beam with these kind of feed elements, and we can steer the beam by changing this angle theta. This angle theta is being controlled electronically from the two planes. And we can form a beam not only in one direction but in several directions. You can just imagine if it is a beam, and if it is a vertical axis, the beam can rotate something like this. As Professor Paul said, that we can rotate up to 30 degrees with this with respect to vertical axis. We call it a broad direction. And not only that, we can steer the beam like this. So we have such kind of thing where the elevation angle is fixed. When we have such kind of rotation of the beam, one beam I am talking about, we have an elevation angle fixed, and when we have such kind of thing, we have changing in the azimuth angle. So both the things can be done in a real-time basis. And the beauty of this radar is that not only a single beam can be formed, multiple beams like a flower you can put. So So that when suppose we beam this up, and if these are the targets, these lines are the targets, so each of the beam is going, and it backs, the reflection comes back, again going another beam, reflection comes back, and you assimilate all the reflections in your receiver and then you do signal processing. So it's a very, very complicated thing. In a standard way, you have to gather those reflections, ensure that these reflections is sufficiently energy sufficient enough for further processing of the signal, and we can encompass all the targets. And even these beams are not particular positions, you can rotate the beam at different angles and position. So this is how this phase array works. So as I said that the phase array and beamforming is an integral part of this phase array. Forming beams is important, and nowadays you know that we are entering into the 5G era of mobile communications, and you will be and we are very much proud that such kind of phase array beamforming antennas are being used in a mobile communication system. So it's a very, very state-of-the-art system. As I showed one example, when we form such a beam, you see that current situation is that only one beam is radiated from the antenna, and that is being picked up by the different mobile receivers. But here, since you can generate multiple beams, so each of the mobile is not pointed towards one beam. So you can think of such a high, since huge energy is actually pointing towards one mobile, only a single mobile, the data rate increment is enormous. So we can increase the data rate in this fashion. So that is why we are called one of the disruptive technologies that this 5G have. And fortunately we have having this ST ladder which is also functioning the same way. Okay, so one thing is this. So I write a few lines. The electronic steering of the beam is called beamforming. When you rotate the beam like this, then it is responsible for beamforming. Ability to quickly form multiple beams as it is showing. So it improves the target resolution, interference cancellations without changing the array structure. My antenna is fixed, my whole structure is fixed, I am not changing. But I can move the beam as I wish. So I can go to this specific target dimensions. And interference cancellation is a very important point. That means that suppose if some mobile is communicating, you see that it is communicating with this beam only. This signal doesn't interfere with this. So interference cancellation you can do. Suppose if the side looks, the most important thing is that the side look has to be minimized. That is one of the challenges is that these are the side looks which are no useful to us, only the main look which is we are interested with, and this actually gives the target and people is generated out of this. The technique is expensive. You understand there's so much of signal processing, so much of technology, so much of components are required to realize such kind of phased array system. The technique is very expensive and costly, but increasingly affordable as power of computation is being increased day by day. That is why we do not think of that we can really build such a system, because the power of computation has been grown up tremendously. And the technique is increasing, as I said, that it is being also used in some other applications like 5G and etc. So here, it is a ST ladder which contains 455 elements, as the last video shows repeatedly this antenna array. This is the thing which is being focused, and each of these red dots you see here is an antenna element. One such antenna element showing by the red dots is like this. It is a DRD antenna. This is a dipole element. One is the reflector and another is the dipole. So we will guide the beam to one antenna. But since the antenna are in array, they are placed in array. For example, I have shown one such hexagonal structure here separately. With this help of the array and the angle, we can form a beam which we can steer. Similarly, we have so many of hexagons, 25 numbers of almost hexagons are here. So each will form a beam which we can control, and each of the beam you see is being shown here. So all 25 arrays are creating such beams, which we call beam formats. And these are going to the targets. Maybe some irregularities are there in the atmosphere, which hits back. You see the blue light going up, and it hits back the input with the yellow color light, and is picked up and being processed in the receiver. Detects such an. This is the basic essence of beam format. I will show you one by one each of the structure. I am not going to discuss elaborately because the DLB antenna type element is well known to all of us. But the most important thing is that how we can handle such a huge data and process it. That is one of the most important challenges. So you see that full of communications is involved and full of signal processing is involved. And that is why we call it a state-of-the-art technology. So it comes to the second point, that phase data structure which we have in our ionospheric station is something like that. Here each of these array which I shown here by the triangle is actually is one hexagon. I am just representing one hexagon here with one triangle. So it means it's a subarray of antennas. It's another subarray, like 25 subarrays I am drawing here, which is a bidirectional. That means it can send the signal, it can receive the signal, which is bidirectional. And we have a transceiver. That means we can transmit the signal blue line, and we can receive the signal by yellow line like this. So I am not going to details. This is a contact type duplexer which we can utilize here for transmitting and receiving. The signal which is coming here with a switch, it can go and amplify and radiate it, and the received signal which is coming back here comes here with a low noise amplifier. We put the signal to noise ratio here, and with the switch here we can receive it and going to the receiver. So signal once coming back going to the receiver, and the signal which we are transmitting is generated from the exciter and goes back and goes to the receiver. So the whole architecture can be summarized in this way, that full antenna which is shown here, a big thing, can be summarized into this way, that we have such kind of transceiver, and these are the antennas, and we have a elaborate receiver and exciter. Exciters are for transmitter and receiver is for signal processing. So we will be interested to see these receivers, how the signal will be processed, and those who are know a little bit of signal processing will be really astonished that such things are handling so beautifully. So let's come to the more about the linear phase antenna. So these are the elements as I showed earlier, and you see the wavefront which is coming there like this. Each of the antenna elements has a different phase based on the antenna position. So you see that if this is a D and this is angle theta, then the path difference is D sin theta. This is the path difference between the two elements. Everywhere the path difference is D sin theta with respect to this wavefront. And if the path difference is D sin theta, then we have phase shift phi occurring between the antenna elements. So this is the progressive phase shifts which actually help responsible to form a beam. This is the basics of the beam forming. The beam is formed because of this progressive phase shift between the antenna elements. And since the theta can be controlled all from my exciter stage, from the remote side I can control the beam angle. Okay, so this is how it works. And here a little bit about these antenna elements. If I have a single antenna, we have a circular kind of radiating pattern. You have two elements, increasing elements twice. You have a more direct radiation pattern. If you have four antenna elements, you have more directivity. So you see the directivity of the radiation pattern is increasing from 0 dB, 3 dB to 6 dB and so on. So why we are interested to increase the directivity? That is the point I am saying. This is because if we make the beam very narrow and directive, the antenna power which is actually pumping the signal will be very less. Otherwise, if the beam is something like this, we need a huge power to pump the signal and go into the beam. So if it is very directive, so 6 dB gain already is achieving by only 4 elements. We have 19 elements in one hexagon, so you can see the good directivity is already formed in the beam, and that much less antenna power is required. Because I will show you the antenna is not counting continuously like that. It is a small, very fractional deviation, say of the order of 5 to 10 only microseconds, even less, 1 microsecond. It is only transmitting. Then it is switched off. I am transmitting and switched off and waiting for my input to come back. Again I am sending another 1 microsecond signal, again waiting, coming to this input back. And then I integrate all these echoes and make the signal enough strength so that I can detect it. That is the basic behind this receiver's architecture. So this is, you see that the antenna gain becomes very important. That is why in one hexagonal pattern we have 19 elements of antenna, so that we can make the type even not only a single column. If I increase the number of columns like this, I have shown in the previous slide only one column. See, it's only one column or one row you can say. So you can just make it horizontal or you can make it vertical. If it is like this, then we can increase the number of columns, because as you see the antenna structure, it is a hexagonal structure, it is a two-dimensional pattern. So we have a two-dimensional pattern. So what is it? The outcome that we have a half-power gateway. You see that if it is a one column, the signal is something like this. Radiation pattern, if it is two columns, it is like this. If it is four columns, it is more time. So we actually make a more dynamic pattern by using a hexagonal two-dimensional antenna. So this is nothing but making the beam more directional. The half-wave beam width is very narrow, of the order of only 7 degrees or something like that, so that it can hit the target and the echoes can be generated. That is the basic case. So even not only the antenna columns and elements is important, but also the antenna spacing. That means the spacing between the two elements is also very important. So why the spacing? You see that I have tried to avoid the balance, and lambda is the wavelength which is propagating. So if d by lambda is a fraction, then only we can have a very less number of sine waves. But if you don't omit this d by lambda as a fraction, like this, if we have 2 lambda, d equal to 2 lambda, so you see that d equal to 2 lambda, these are true. So that means it doesn't go in. That means more number of beams are formed in the other direction. So what is the drawback of doing more number of beams in the other direction? It takes away the power of the main beam to the other direction, which is useless. So that is why the antenna spacing is also plays a very important part. By designing such kind of array, you have to take it to know that the number of arrays and as well as the number of columns as well as the spacing between the antennas, all is taken into consideration so that we can have a very good sharp beam with less number of sides. That is the main objective of designing such antennas. So here is the beam forming technique I am showing. They are divided into 3 parts. It could be analog beam forming, it is a digital, or it could be a hybrid. I am putting a question whether such kinds of phased array data is the first of its kind in the present generation. The answer will be no. Even 40 years, even not 40, 25 years back, I had gone to the literature and University of California, they have already built up. I will show you one applications what they have got. So they have already built up this phased array data. So what is the difference between what they have built up at 25 years back and now we are building? The difference is that those beam formings is analog in nature. That means all the phase shifts which is actually used by those beamformers are present in analog in nature. But now we are coming out of the analog and making fully digital. So that is the advantage, that the resolution of the targets becomes more accurate now, so that each of the irregularities which is forming in the atmosphere or somewhere can be tracked down more accurately. Okay, so I will just go very quickly about this 3 beamforming structure. One is the analog beamforming. Analog beamforming is very simple. This is the digital signal which we want to transmit here. This is going to one chain, and then we have a splitter, and with the splitter we have a phase shifter. This is a phase shifter. We provide the phase angle phi, and it is going to different arrays to steer the beam. So we have an analog vision, which is not so accurate, the analog vision. And that is why it is called the analog beamforming. Earlier works are based on such kind of analog beamforming. Now currently the digital beamforming is that instead of one single chain, we have multiple chains. Like that we have shown the antenna structure. We have several hexagons, like 25 hexagons. That means each of the hexagon is now fed with one RF line here. And they are going here and going to one antenna array, another antenna array. Each of these actually representing one hexagon. Okay? So to be more clear, that here I am showing that one RF chain is coming here, and with the help of the speaker, it is captured the needs of one hexagon. So one hexagon is something like this. So one RF line will come here and feed all the antenna elements in one hexagon. So similarly, another RF line will come here and feed another hexagon. So we see that the beam is formed at different angles, so that the whole horizon can be covered with very sharp beams. So that means we can form really the multiple beams. That is the biggest advantage of such kind of phase-like system. Now this is what I am introducing this slide, that phase array radar transmit receiver system. When you transmit this, it actually reflects back the signal. And suppose it is transmitted and it is reflected back, and our aim is to maximize the reflected echo coming from this direction, because these echoes can go in a here and there. But the processing should be such that most of the echoes which is coming here can be absorbed and can be processed, and we can make the energy sufficient so that we can detect those echoes. That is the basic idea. That is, I put this area where all the echoes which is coming in this line, in this region, will be collected by the receiver and then processed successfully. So here is the transmitter. I am showing the height or range measured with nanopulse is equal. As I said, that the transmitter is not a continuous wave, rather it is a pulse. That means a small pulse is being transmitted, and it is only 0.5 to 1 microseconds. Maybe it can be adjusted to be more bigger or maybe smaller. And then it is received, then it is stopped, and we are waiting for echoes to come. You see the target, it is going and hit the target, and echoes are generated, and echoes are coming back to the receiver. So I am not going to detail about what is the range resolution and other things, because these two echoes actually differentiate that how these two echoes can be closed, so that we can differentiate these two echoes. That is, these two delta. I say I am not going to that detail, but rather what I wanted to mention that this transmitted pulse is not a single pulse. It is also a coded pulse. We use a 8-bit binary coded signal, so that the reflected echo is also having its signature, so that we can extract the echo in our receiver with more robustness and more synchronization can be carried out with reduced error. So all these advantages will come if we make this transmitted pulse coded, and that is why we make 8-bit binary coded, just like a line coding we employ in our communication system is also similarly coded. This transmitting pulse is coded, and so the received echo is coded, and we can extract it. So there are two ways we can connect these echoes. One is utilizing the matched filter. So matched filter means that the transmitted the pattern of the received echoes are known to the receiver, and when this is correlated with the maximum correlated with the transmitted pulse, we get a high peak. So we know that the echoes has come. But this is a very old technique. Many people are utilizing this matched filter technique in the radar system. But in this case, we are doing the spatial filtering, not the matched filtering method, spatial filtering techniques to receive this beamforming target. Okay? So I will show you what is the spatial filtering and how it is done. So another important point to tell that it is a Doppler shift, because when suppose I want to find a moving target, suppose I can plane or moving, or the convective cloud is moving in vertical directions. That means when the signal is hitting this target, as the target is moving, the reflected signal will have different frequency shift. We call it a Doppler shift. So that means that if the signal transmitted is F0, the reflected signal signal will be f0 plus minus ft, which is the Doppler shift, f0 and f0 plus minus ft. So the return signal will have a Doppler signature f0 plus minus ft, and when we feed these two signals in our receiver, we get the information about our Doppler frequency shift. So once we put the Doppler frequency shift into this equation, we can find the other things are known because theta is known, which direction I am sending the beam is known. The lambda is a wavelength transmitted. So once I calculate this ft, then we can calculate the velocity v orbital. That means the convective cloud is moving away, its velocity can be detected with the help of these equations. So the second part, so first part I have completed the received array, the received antenna array, how it goes. The second two important point is the receiver, that is called the beamforming receiver. The digital, there are two important components here. One is called digital down converter, and another is called the baseband digital signal processor. What is digital down converter? It actually consists of three stages. One is the RF stages, and then the intermediate frequency stage, and then we do the analog to digital converter, the sampling. So these are the two things I will discuss: the digital down converter, which converts the radio frequency signals to the baseband numbers. I have two form, I will tell you what is my phase and quadrature form digital signals. The second portion is the spatial filtering, which I will explain, not mathematically but rather physically, how the Zephir filtering is carried out in this case to recover the stars that I will explain. So Zephir filtering is complex weight multiplications and addition of signals is carried out in the spatial filtering. So this is how in one simplified way I describe the digital down converter. This is, you see that the signal is being, the RF signal, if you see if it is the equation, it will be called j omega RFT minus theta. So it means it is the RF signal. In our case, it is a 53 megahertz signal which is received by the antenna elements. And this theta is very important. This is the phase shifts offered due to hitting the target and the signal is coming back. So this theta n extraction is very important. Otherwise, when you add up all these signals, then it is possible that because of the different phase, they can cancel out and I am not getting anything out of it. So that is why this theta has to be estimated, and this theta is estimated in this way. The signal which is entering into my antenna is I am just doing a multiplication with another local oscillator frequency to make it an intermediate frequency. The frequency is much less than the RF. If the frequency is less than the RF frequency, it is possible that I can do the sampling at a much lower rate compared to the signal which is coming in the RF stage. RF is almost, it is 53 megahertz. That means to have the Nyquist criteria, I at least have more than 100 megahertz sampling rate. And as you know, that if the sampling rate of the ADC is increased, the cost of the device goes on increasing. So I cannot do that thing. That's why I convert it into IF signal and then do the sampling, so that the signal can be converted into a discrete signal. You see, these are not just like numbers. Here you see I have the T, the time domain information, but here it is only a numbers. The signal is only numbers here. And these discrete signals are now made in phase and quadrature component just by multiplying it with the cosine terms and with the low pass filter and the sine term with this and with the low pass filter. I can make I and Q form. The most important thing is to know that here the theta phase is in the argument, but here it is in the amplitude. So I convert this theta from the argument to the amplitude, and it is much easier to detect the estimate is theta in this. So the function of the digital down converter is to take the RF signal and convert it then in digital in phase and quadrature form. So this is the basic part of it. Signal, so that means I can bring the signal from RF stage to the baseband state, what is simply the frequency not involved. Now the second one is the spatial filtering. Once I receive this signal, now I can go for a filtering. Here I am not going to detail about the filtering procedure. It involves a lot of signal processing knowledge. Now what I can tell you that if I have a single antenna in this whole hexagon, as I told you earlier, that our antenna array consists of 25 hexagons like this. So if I put one antenna at the middle of in this hexagon and I put this filtering after this, FR filter after this, then the output will also show some special informations of the area around it. Instead of doing this, why we are putting more antenna instead of single antenna? Because we want to get information of the spatial places more accurately. So instead of doing this time delay phase shift by phi, what I am doing by utilizing several antennas, that these red dots are actually these antennas like this, and we have a delay of phase shift as I explained earlier. These are entering to this, and the same FIR filtering is also carried out here. And this whole process I get the same output as I am getting here. But the advantage of doing this with many antenna array is that the resolution of this might be about things of both the spatial information in this hexagon. That is the basic advantage of this structure, and that is why we have moved several antenna elements in one hexagon. Okay, so this is, so if I again see this structure, you see that the signal elements are coming here, all the x vectors are here, and we are actually sending these x vectors into our system, which consisting of these weight elements. These are the weight elements, which is basically some kind of optimization is there. We have to find out these weight elements with the help of some optimization elements. So that means if I get the output y, it becomes a convolution of the input and the system which consists of these weights. So I just put it in this way here. You see that x input vectors are entering into a system which consisting of so many weights, and the output is a convolution between the input and the source. So instead of this convolution operation is very cumbersome because it is a time domain operation. So we can circumvent this operation by going into the frequency domain. So what we do, this x vector which is in time domain is converted into the DFT. So we apply the DFT algorithm here to convert these x signals into a DFT points, and similarly W is also converted by DFT into the frequency domain. And instead of doing convolution, we can simply multiply these two, and doing the IDFT, we get the same output y which is obtained here. But what is the advantage of doing such kind of effective operations here? Because if we consider the lower computational complexity. A lot of computational complexity will be involved if I do these operations. But if I do such kind of DFT operations, the computational complexity is reduced drastically. That is the biggest advantage of doing the computation in the frequency domain. And I am going to skip into this mathematical thing. Weight vector which I have just shown here earlier, we can estimate these weight vectors by different techniques or maximum vector techniques. So these are the techniques which we utilize to find out these weights. So once we find out the weights and the input signal, we can find out the output of such a signal. So we have one kind of simulations we have done there, and we have shown that we can form a beam at 40-degree angle. Here is the original beam, it's at 0 degree. Now utilizing such techniques, we can shift the beam and, for example, 40 degree. And this is the final slide I am showing is the applications of the ST ladder, elaborately told by Professor Paul. Here I am showing because as I told you that such kind of phase ladder has been built up much 20-25 years back, but with the analog technique. And there you see that the beam is formed with such kind of analog technique, and they estimate the time, height, cross section of the wind profile in the atmosphere. You see that this is the time, and this is the altitude of the lines. So you see, and these are the lines, the profiles which is showing the wind, vertical wind component. The wind is moving upward, like a convection wind is going up. So this can be calculated. You see that as we go height from 4, 6 to 8, 10 kilometers, the wind velocity is increasing from 10, 20, 30, 40, 50 to 60 meters per second. And then we even go height from 8, 12 and 14 kilometers is again reduced. So such kind of data has already been taken in 1976. That is why I am telling you such kind of structures already been designed well there. But the advantage of the present system is that we can do such kind of exercise in a more accurate fashion. Even with a small target area, small irregularity formed inside can be detected with the help of such kind of glacier. And such kind of application is possible.